Okay, so this is my entry to Sly Sparkane's perspective challenge. So Sly issued a flat earther perspective challenge yesterday. I haven't been able to get around to it until today, but I'm going to be looking at this now. I've kind of thought about how I'm going to do this, but I'll be doing it live, doing the calculations live, so we can hopefully see if I'm working it out right and if I'm correct. So the challenge is that there's a ball at an unknown distance away from the camera. The camera then pans down and shows a ruler, which is 128.6 centimeters from the camera. Then the camera dollies 150 centimeters right to retain the same angle in the zoom to that point here. And you see the ball move across. So what he's looking for is the distance of the white ball and the circumference of the white ball. Now, I'm not a flat earther. I'm a dedicated glober, but I like this sort of challenge. I love this kind of math, so I wanted to see if I could get close, and I'll submit this to Sly. I'm going to keep the video unlisted until Sly releases the results, and then we'll release the video hopefully if I'm at least fairly close. So we'll see. All right, so how have I approached this? I've drawn this out a little bit here. So here there's the ruler, which we know is 128.6 centimeters from the camera, and I've drawn this out here. First of all, we want to work out what the hang on, here we go. There's the camera, there's the ball. Let's move a bit closer to the wall. There we go. And here is the ruler. So we know this is 128.6 centimeters from the camera here, and this is actually millimeters rather than centimeters. So you know what, I'm going to make this millimeters as well. So 1,286 millimeters, and I've counted up the millimeters in this ruler. Is 113, and then on the right there it looks like about half a millimeter. So I'm going to say it's 113.5 millimeters on that ruler. So first thing we want to do is try and work out what this angle of view is. The camera is obviously zoomed in quite a way, so it's going to be a relatively narrow angle. So the way to do that is we have here effectively two right angle triangles, and we know that the width of we want to work out this full angle here, so we're going to take one of these angles and work out what it is and then multiply it by 2. So the opposite to that angle is 56.75 millimeters, and the adjacent side is 1,286 millimeters. So get the calculator up. To do this, it's opposite over adjacent, so we're going to use tangent. So let me clear this off. All right. So the tangent of this angle is opposite over adjacent, so 56.75 divided by 1,286, and then we need the inverse tangent to get the angle. So the angle is 2.52 degrees. We'll multiply that by 2 to get the full angle. Okay, so the angle is 5 degrees in total, just over. So let's take that to, I don't know, a few decimal places. Copy that out. There we go. I'll just write that in. So we have, that is our total angle. Which is this angle here, our view angle basically. So we're seeing 5 degrees across our across the total width of the image. So let's go to the images of the ball in both positions. So I've put those into Photoshop already. So here we've got the screen grab of the ball in the first position, and then on another layer a screen grab of the ball in the second position. Just zoom out. Okay, so there's the full image. Now the image size is 1919 pixels wide. So if I measure, so we know that this is 1919 pixels wide and that it's just over 5 degrees viewing angle total. So if we can then now determine how far the ball moves from one scene to the next and work that as a proportion of this total viewing angle, we can work out the angle that the ball moves across the frame. So I've put a couple of guidelines in. I put one at the front of the ball. I want to work out the distance between distance to the ball is the first thing we're trying to work out, and there is a little black dot Sly spot on the front of the ball, which is very helpful. So our guideline wants to just be centered on that black dot there, and in this image, same thing. Okay, that's pretty central. So it's yep, those two lines there. So if I now look at the pixel width between those two lines, let's just draw a box. So the width is 758 pixels. So grab our calculator. So 758 divided by 1919. So that's 0.39 something of the total box width, and there was our angle. So let's now multiply that by the total angle. So 5.05354. That will be enough. So the ball has moved 2 degrees. Yep, bang on 2 degrees to 3 decimal places. Actually, no, 3 decimal places, it's 1.996. Let's keep it 1.996 just to make it as awkward as possible. So the total distance the ball has moved is 1.996. I've drawn this out like this. So we now know that the camera dollies from this position to this position, which is 150 centimeters. We're trying to work out this distance here, the distance to the ball. And if from a position directly in front of the viewing point of the camera, it's not directly in front of the camera, it's directly in front of part of the frame, but it moves 2 degrees from one part of the frame to the other. So we know that this angle here is 2 degrees, and hence this angle here is also 2 degrees, 1.996 actually. So the sum we need to do is, I'll write this out. So again, we're going to use tangent because we have the opposite side and we want to work out the adjacent. So the tan of 1.996 is equal to 150 divided by adjacent. So just rearranging that to make adjacent the subject. So adjacent equal 150 divided by the tangent of 1.6. Okay, so back to the calculator. So 150 divided by
open brackets, 1.996 10, close brackets, equals. Okay, so 4,304 centimeters, which is 43 meters. Wow, that is our distance to the ball. 43.04 meters. But let's put this on a separate slide. So these are our results. So distance to the ball, 43.04 meters. Now we need to work out the circumference of the ball. To do that, first of all, we need to work out the diameter of the ball. So we know a lot of this information now. We know the total angular width, which is that. We need to work out now the angular width of the ball. So back to Photoshop. So if I work out the angular width, I've got two lines drawn here, one on either side of the ball, the diameter. So drawing this line again, this box, should I say? It's not on the guidelines. Okay, let's try that again. Okay, this will do. If I get it just on this side, then that'll be right. So the width is 99 pixels. Oops. Okay. 99 pixels wide for the ball. So back to here. I need to work that out now as a proportion of the whole width. So 99 divided by 1919 is that. And now we'll multiply that by the angle, which was that 5. There we go. Times 5.05354. So that's the angular width of the ball. 0.2607. So if I go to I'm going to use an angular size calculator because I'm lazy. So I want to resolve the size. I want to know the size of the ball. So I'm going to go by size. The angle in degrees is, just copy that in. And the distance is, where's the distance? 43.04. 43. Do you know what? I'm going to put it in centimeters. 4304 centimeters, because the ball then will be in centimeters. The width of the ball I have as 19.6 centimeters diameter. So if it's 19.584 centimeters diameter, multiply that by pi, and we'll have the circumference. So I've got a 61.52 centimeter circumference. 61.52. Centimeters. Okay, so that's it. That's the figures that I've got. 43.04 meters to the ball, and 61.52 centimeters for the circumference of the ball. There's a few areas where this could have fallen down. This didn't have tenths of millimeters on it, and just a slight variation here could have thrown things out a little bit. The ball is obviously a little distance. The measurements I was taking, excuse me, were to the front of the ball. If I was being really pedantic about it, I could measure in Photoshop the angular distance from the side of the ball for the second measurement to work out the diameter, because you're measuring when you're working at angular size, you're measuring to the center of the sphere, not the front edge. But with a 20 centimeter diameter ball at 43 meters away, it's not going to make a massive difference. That extra 10 centimeters of distance. So, but when it moves across the screen, you'll get a slightly different figure because of parallax. The front will move a little bit further than the side. But I think I'm not going to go any further with that. I think that's enough. And just to kind of sense check it, if the ball is 20 centimeters in diameter, let's go back to the video here. So let's just have another look at that. So if that's 20 centimeters in diameter, then there's obviously a door frame behind it. So that means that that door frame is what, about a third of the width of the ball, which would make the door frame about 7 centimeters or so. And it looks like quite a narrow door frame. So yeah, 7 centimeters seems about right. Again, just as a sense check. Yeah, I'm pretty happy with that. I was surprised it was 42 meters distance away. But assuming that Sly's figures are right with that ruler is in centimeters, which obviously it is, and that the ruler is 128 centimeters from the camera, it must be zoomed in a long, long way to have only 11 or whatever that is. I've forgotten, 11 centimeters or so side to side in the frame. So that shows why the angle of view is so narrow, and also why this is so kind of jerky. You can see the heat haze there on the ground, and it's not steadiest of pictures, which kind of surprised me from Sly. This explains it. If he zoomed in over 40 odd meters away, then that kind of explains that. So there we go. Sly, thank you for that challenge. It was really fun. I enjoyed doing that. I hope I'm at least vaguely close. And yeah, thanks again. Let's see if any flat earthers get anywhere near the correct answer. Cheers. Bye.